Hello everybody, good morning. So in our earlier classes we have discussed about the electrophilic aromatic substitution reactions. So today let us take up nucleophilic aromatic substitution reactions. So we know that benzene is a consequence of the 5 electrons above and below the rings. There benzene exists as a nucleophile. So benzene, I can write down here, benzene is a consequence of 5 electrons, above and below the plane of its ring, Benzene is a nucleophile. Okay, so we have already discussed earlier also about this. Okay, benzene as a consequence of the pi electrons above and below the plane of its ring is acting as a nucleophile. So suppose benzene can undergo this hydrogen is there and reacts with nucleophile. The reaction doesn't go because it already cell is a nucleophiles cannot attack here. Okay, because benzene itself is a nucleophile. So is also electron rich, so they are repelled. So benzene generally can have this earlier have also told about the delocalization pi electrons. Pi electrons are delocalized above and below the plane of the rings. Okay, so here p orbitals. So pi electrons are delocalized above and then below the plane of the rings. Okay, so below the plane of the rings. So this is why pi electrons are delocalized above and below the plane of the ring. So that is why nucleophile, which is an electron rich, cannot attack here because already electrons are delocalizing here. This is why benzene does not react with nucleophile, does not undergo nucleophilic substitution reaction under normal condition, okay, standard reaction condition, because of this fly route. I will write down here. So the benzene does not react with nucleophiles under normal conditions, or you can say under standard reaction conditions, under standard reaction conditions. Okay, reaction conditions. So normally benzene does not react with nucleophile because of these pi electrons delocalized above and below the plane, because the pi electrons clouds repel the approach of as the pi electrons clouds repel the approach nucleophile. Okay, approach nucleophile, approach of a nucleophile, you say, approach of a nucleophile. So they repel each other, nucleophile. Okay, and thus approach of nucleophile, and thus living group will be very strong basic conditions. So that's why benzene itself is a nucleophile. So normally in normal conditions this benzene doesn't undergo nucleophilic aromatic substitution reactions. However, if the benzene ring has one or more substituents that strongly withdraw the electrons from the ring by resonance, then the nucleophilic substitution reaction may take place. Okay, nucleophilic aromatic substitution may take place. I'm repeating again. However, if the benzene ring has one or more substituents that strongly withdraws electrons from the ring by resonance, and along with a good leveling group such as halogen, then electrophilic aromatic or nucleophilic aromatic substitution reaction may take place. So I write that here. However, However, if the benzene ring has a one or more substituents, okay, substituents that strongly withdraw electrons from the ring by resonance. This is one. If they have strongly electron withdrawing groups in the benzene rings, then another step, and a good Levin groove present in the good Levin groove. So like halogens groups, like such as halogen. Then nucleophilic, aromatic, aromatic substitution reactions may take place. Okay, may take place. So I'm repeating again. If the benzene ring has a one or more substituents that strongly withdraw electrons from the ring by resonance, and also having a good Levin group, then nucleophilic aromatic substitution reactions may occur without, say, at normal condition, without using extreme conditions. Okay, in normal condition can take place. So the electron withdrawing groups must be positioned at the ortho and para positions. The electron withdrawing groups ring must be at the ortho and para position. Must be positioned at ortho or para positions of the Levin groove. Para positions of the Levin group. Okay, Levin groove. Say halogen here, halogen. Okay, in this case halogen. Okay. So the greater the number of electron withdrawing groups, the number of electron substituent, easier it is to carry out the nucleophilic aromatic substituent. If the number of electron withdrawing groups are more, then it is easier to carry out the nucleophilic aromatic substitution reactions. So I will give one examples here. Some examples I will give here. So nucleophilic aromatic substitution can undergo when if electron withdrawing groups are present in the aromatic ring with a good Levin group. For example, say this compound, chlorine here, chlorine is a Levin group and nitro group in the para positions. Then reaction takes place, and suppose reaction with sodium hydroxide or always hydroxyl group, then nucleophile, and then this is temperature at around 160 degrees, then followed by acidification, wag off with it. Then we got us refresh chloride. Chlorine is refreshed by OH, and then this nitro group, and then we have ICl. Okay. If the number of nitro groups is increased, suppose it is increased to ortho and para positions, chlorine, another groups at ortho position NO2 and para position 2 nitro group, dinitro-chlorobenzene, then same reactions. OH, your pH is around value greater than 4, and here around pH is greater than around 10. pH is around 10. Okay, around 10. Okay, then you can the temperature will be reduced. So temperature is from here 162 now 100 degrees Celsius, and the product will be OH, as is ortho position, the nitro groups are ortho and para groups. Okay, plus ice chloride. Okay, so this is another way. There are 3 nitro groups present, then we can have another, say, reactions, say chlorine, 3 nitro groups. trinitro groups, NO2, NO2. So more increasing the reaction condition also become decreases also, like water around pH is normal 7. Water reacts with 40 degrees Celsius. So it is normal condition of standard conditions. So temperatures decreasing from 160, 100 degree, 40 degree as number of electron withdrawing groups are increases. So here product will be, so OH here, then NO2, then we have NO2, then we have NO2 here. 3 nitro groups are present. So I'm giving example that the number of electron withdrawing groups increases, and then the reaction condition also in favorable conditions comes. So here, so I'm again repeating that electron withdrawing substituents increase the reactivity of benzene ring towards nucleophilic substituents. However, it decreases the reactivity of the benzene ring towards electrophilic substitution. So electron with number of electron withdrawing groups increases, then it is the benzene ring nucleophilic aromatic substitution reaction is increased. The rate of the nucleophilic substitution reaction increases. However, the reactivity of the benzene ring towards electrophilic substitution reactions decreases. Okay, I'll write down here. Okay. Thus, any substituent that deactivates the ring towards electrophilic substitution activates the ring towards nucleophilic substitution. So I can write down here electron withdrawing substituents, okay, increase the reactivity of the benzene ring, towards nucleophilic substitution reaction, nucleophilic substitution, and decrease the substitution and decrease the electrophilic substitution. Okay, substitution. So I'm repeating again. In the case of the benzene ring has electron withdrawing substituents, then the rate of the reaction towards the nucleophilic reaction is increases. However, the reaction towards the rate of the decrease towards the electrophilic substitution reactions. Decrease the reactivity of the, you can say decrease the reactivity of the benzene ring towards the electrophilic substitution. You can say decrease the reactivity of the benzene ring towards decrease the reactivity of the benzene ring towards the reactivity of the benzene ring towards the electrophilic substitution. So here the electrophilic substitution, another one is nucleophilic substitution. So electron withdrawing group substituents increase the reactivity of the nucleophilic substitution, however decrease the reactivity of the electrophilic substitution. So thus any substituent that deactivates the ring towards electrophilic substitution activates the ring towards nucleophilic substitution reactions, and vice versa. So we can say that this type of reactions, nucleophilic substitution, aromatic substitution reactions, can take place in two systems. So first one we are discussing this about the first is this one is addition followed by elimination. Another one is reaction you can have elimination followed by addition. Okay, so I write down here generally nucleophilic substitution reaction of the aromatic substitution reaction can take place by two ways. Okay, by two possibilities or two cases. So I write down here nucleophilic aromatic substitution reactions can take place in two cases. Possibilities are in two cases. First one is, so you can say nucleophilic aromatic substitution reaction can take place by two way. Okay, two cases are here. By two ways. First one is this one is addition followed by elimination. Okay, addition, mechanism of the reactions. Addition, the mechanism of nucleophilic aromatic substitution reaction can take place in two ways. Addition followed by elimination. And in the second case, is elimination followed by addition. Okay, so we can, the mechanism of the nucleophilic aromatic substitution reactions may take place by two cases. First one is addition followed by elimination, and second one is elimination followed by addition. So the example we have given the earlier one. In the first case is that just now we have given the one is the reaction by chlorine nitrochlorobenzene by this nucleophile is the addition followed by elimination. Okay, so we will write down here mechanism of the reactions. First case is write down addition followed by elimination. Mechanism of nucleophilic reaction, addition followed by elimination. So the first one, so let's say generally, okay, I write down here. Then this is the leaving group, and this is the nitro groups here in the para position, let us say. So now nucleophile in the negative attacks to the addition takes place. Addition then takes place. Okay, so we have the slow process, the mechanism of the reactions. The addition takes place first. So we can have this is nucleophile, then leaving groups. Okay, then the negative charge here. Then we have this nitro groups. NO or negative charge. Okay, so this is nitro groups. Now this positive charge here. Then this nitro groups we have positive charge here. Okay, then this one can delocalize this negative charge, then can be delocalized back again. This one here in this way, or you can write this way. Okay, first it can be here negative charge here, or they can delocalize again here like this. Okay, so this will be the another resonance structures. Okay, nucleophile, leaving group. So addition first takes place. In this case, we have addition takes place. O negative. Okay, this can come back again. This can come like this. Okay, so we can write another resonance structure, so on. So we can have nucleophile, leaving groups. Then we have nitro groups, NO2, like, okay, this is nitro groups. So this way you can have resonance structure, many resonance structures. Then this can be, and so on. Another can be delocalized again this way. So this, so now this finally this second step is lost by this one. So this one, let's say this is the second step, elimination takes place. Okay, first is the negative charge, let's say here, the nitro groups. Okay, so then leaving groups elimination takes place. So here, then we got a product. Okay, this is very fast reactions, slow. So here, like this also, the leaving group goes. Then we have nucleophile substituent here. Then we have this nitro groups. So this is a mechanism of the nucleophilic aromatic substitution reactions. So it is in the case of here is, I'm showing here is the addition followed by elimination. Okay, so the mechanism of the reaction is addition followed by elimination. Okay, here the mechanism of the reaction is first addition, and then nucleophile is added, then then leaving group is eliminated in the second case. Okay, so here is the second case is the second case is the elimination followed by addition. Okay, second case is elimination followed by addition. Okay, so in the earlier case, earlier mechanism was addition followed by elimination. Here we can have second case is elimination followed by addition. This is mostly used in the benzene mechanism. Okay, this benzene mechanism. So one example is when chlorobenzene, say chlorobenzene can react with sodium, a very strong base, sodium amide in presence of ammonia at very low temperature. So they give aniline. Okay, aniline. So this is one example for addition followed by elimination. So here I can write chlorobenzene can react with chlorobenzene can react with sodium amide, a strong base, extremely strong base, to give aniline. Okay, at very low temperature, at minus 30 degrees Celsius. So this is one example of the reaction for elimination followed by addition. So we can have the mechanism of the reactions. Okay, let us see the mechanism of the reactions. So here mechanism of the reaction. So first this hydrogen here, so the might a strong base, abstract the proton. So you can give the minus negative here, or you can go like this, first step by step. Let's say, so chlorine here, then negative charge here, then again this loss, this is a chlorine, then we have a benzene intermediate. Okay, this benzene intermediate, this benzene intermediate, this can second step can have this. So here elimination, first leaving group is eliminated followed by this. Now nucleophile followed by nucleophile attacks. Okay, followed by addition in presence of ammonia, followed by additions. So we can have this NH2, then pick up the proton from the liquid ammonia, then we have this final product. Okay. So what I am telling that this nucleophilic aromatic substitution, in the second case, first elimination followed by addition. So here the chloride leaving group is eliminated first to give a benzene intermediate, then this benzene intermediate can be reacted by nucleophile to give this product. After I pick up the proton from here, so we got this one. So this is the second case of elimination followed by addition. So this elimination benzene can also be affected by having substituents either in the substituent, then we can have different products. Okay, like earlier cases, here we'll have different reactivity and substituents of the natural substance will come in the benzene mechanism. So let's say okay, I will write down here. If the Z is a substituents, either maybe electron withdrawing group or electron donating groups. Suppose Z here, then we have a leaving group here in the ortho positions. Then if we lost this one here, lost by, then we have benzene can form here. Benzene, first elimination will form this one. benzene will be formed here. This benzene. Another one, when here one hydrogen air cap and this one, so you can have this one. Another one, if this meta positions, then this hydrogen, it can be clipped like this hydrogen. Here this hydrogen lost and this go down. But here in this, there are two cases. Now two products can be formed, either here or here. So we can have two benzene intermediates in this case. So you can have either here and plus another one will be. So you lost this one, then we have triple bond here. Okay, like this. So two benzenes can form in the. So let's say 1, 2, 3. Here 2, 3, and here 3 and 4. Okay. So another one is the case of leaving group is in the para positions. So leaving group is para positions. So here hydrogen. So you can have here or here. The loss can benzene formation is same. Okay. So here benzene can be formed here, either here or here same. So only one benzene mechanism, benzene intermediate is formed. So except meta position, in meta position, then we have the benzene either at the 2 and 3 or 3 and 4. Okay, but here in the case of ortho, when the living group is ortho position or para position, we have only one benzene intermediate only. In the ortho also only one, para also only one. But in the case of the living group is in meta position, then we have two intermediates of the benzene intermediates. So depending on the nature of Z, either electron withdrawing or electron donating group, then you can have different products. Okay, if it is electron donating groups, then this is more the negative charge will be here. Ortho and para positions are negative charge, so nucleophile can attack. Nucleophile should attack to the meta positions. So nucleophile will attack here when Z is electron donating groups like this. So because ortho position is already electron rich. Similarly here also, either here also same case, we can para position will be electron rich, so it takes the like this. Okay. With the electron donating group, then it is electron withdrawing group, then the another mechanism will come. So these are the activity we have discussed also earlier in the case of reactivity in the electrophilic aromatic substitution reactions. So this is about the nucleophilic aromatic substitution. So I am repeating again. So nucleophilic aromatic substitution. So summarizing the today's class again. So in the case of nucleophilic aromatic substitution reactions, we know that benzene ring itself is a nucleophile because of the presence of pi electrons cloud above and below the ring. So nucleophile cannot attack to the benzene ring because nucleophile is electron rich, benzene ring also electron rich, so they repel each other. That's why generally in normal conditions benzene ring does not undergo nucleophilic aromatic substitution reaction. However, when there is substituents, electron withdrawing groups are present, substituents are present in the benzene rings. So then the nucleophilic aromatic substitution reaction may take place when they have a good leaving group like halogens. Okay, so the number of these electron withdrawing groups are present increases, then the reactivity of the benzene ring of the nucleophilic aromatic substitution increases. However, it decreases the reactivity of the benzene ring to get the electrophilic aromatic substitution reaction. So decrease the reactivity of the electrophilic substitution reaction. So if the number of the electron withdrawing group substituent present in the benzene ring increases, then the nucleophilic aromatic substitution reaction also increases. However, it decreases the electrophilic aromatic substitution. So this is we have discussed earlier. So we have two mechanisms here. First one is elimination followed by addition, and the second one is addition followed by elimination. Okay, so we have two cases. First one is addition followed by elimination. Second case is elimination followed by addition. So we have discussed this thing in the two cases. In the earlier case we have given nitro examples, and then in the second case this is elimination first to get the benzene, then addition takes place. Elimination first, then to remove the leaving group is removed, elimination takes place, then followed by addition of the nucleophile. So this is the benzene mechanism. So this is our so these are about the nucleophilic aromatic substitution reactions. So another one you can say single electron transfer reactions, SEP. I will just I don't know whether it is in the label or not. So we can I'll just give you SEP. Okay, SEP, single electron transfer reaction, single electron transfer SET, S-E-T reaction. Is it reliable or not? Anyway, included in the single syllabus. Okay. So single electron transfer. So there some reactions can be take place by transfer electrons from the metals. Say for example, the benzophenone, when it reacts with the phenyl groups are here, benzophenol, phenyl. Okay. When it reacts sodium, for sometimes it depends on the purification of the this thing also takes place. For example, we add that. So when electron is one from the transfer from here, from the metals transfer electrons, so it gives transfer electrons. So one electron transfer. Okay, so here are sodium positive charge, and then we have this phenyl. So let's say oxygen is 1, 2, 3, 4, 5, 6, 7. Okay, so now you have electrons here. So radical, yeah, radical is formed. Then it's phenyl groups. Okay, so this is we can have this one negative charge here. Then the radical here, radical is a carbon. So radical. This is NR radical. This color is blue. This is NR radical. Color is blue. Anion radical. Okay, anion radical is formed. So single electron transfer from metal electron, and this blue can again another pick up another electrons. I will down here. This phenyl. Okay, oxygen 1, 2, negative charge, and then we have phenyl. Okay, another again pick up another electrons from here. So it is become dianion is formed. Then you have oxygen 2. So okay, this phenyl now it becomes negative charge here. So this purple color. Okay, this color is change. So the reaction is when the reaction takes place. So we can have different changes. So you can say dianion. Okay, 2 anions are groups are here. So it has to be dianion. Then finally the walk off in presence of water, walk off and in water, pouring the water or something, and then we can have this 2 molecules of water will come. Then we have this alcohol. Okay, this pick up hydrogen here. So we have OH, the hydrogen, phenyl. Okay, pick up 2 hydrogen atoms from the water. So we got, so these are electron transfer, single electron transfer reactions. So I'm giving one example. This type of reaction also found in bar reductions. So bar reductions, another example I'll give. The bar reduction, single electron transfer can take place in fact can be found in bar reductions. Okay, when you use sodium, lithium in ammonia reactions. Okay, for example, say benzene rings in reacts with lithium in ammonia. Okay, so we got this dianion system. Product will be cyclohexadiene. Okay, so this is bar reduction. So mechanism is like this. First, it's a 1,4 addition takes place here. So let's see mechanism of the reactions. The single electron transfer takes place here. So let's say this one. Okay, lithium electron transfer from here, 1 electron transfer. See here. Okay. So a negative charge will come here. So here a form, let's say hydrogen here, hydrogen here. So here negative charge, then here. Okay, so this is electron here, anion radicals. Then again this another sodium, you can have dianion. Another electrical electron is given, so it becomes dianion. Okay, so dianion, then pick up work up water or ammonia. The ammonia is used solvent, then you have you take up this. Okay, so product like this. So this is a single electron transfer. So but it is about the bulk reductions. So suppose the substance is there, electron donating group, electron within group, then we can have different. Suppose you have this electron withdrawing group like carboxylic acid, reduction with lithium ammonia, and then another with OCH3 electron withdrawing groups, then we can difference. So the position of double bond and will be different here. So here OCOH, then like this, but in this case be OCH3 like this. Okay, depending on the nature addition text, the mechanism will be different. So this about the simple single electron transfer reaction. So I am giving here whether it is related or not. Anyway, today we have taken this nucleophilic aromatic substitution. So I will wind up for today lecture here. Okay.